Good. I don't need that. Let's use this instead. The new ingredient, for those of you who know what a Freudenthal triple system is a new symmetry that we call Freudenthal duality, which is an anti-evolution which preserves the quartic invariant. And the significance of the quartic invariant from the black hole point of view will be that it provides the Bekenstein-Hawking entropy of the black hole. Now, since this early paper, there have been some more recent developments on extending this notion of a Freudenthal dual. But for today, I'll just focus on its application to quantized black holes. And because the black holes are quantized, we'll not merely be looking at Jordan algebras and Freudenthal triple systems, but integral Jordan algebras and integral Freudenthal triple systems. And we've made use of this mathematics. So classically, black holes are uniquely determined by their mass, charge, and angular momentum. In the quantum theory, they carry an entropy, and it's a dilemma or a challenge to explain from a microscopic point of view what the origin of this entropy is. We're going to be interested in black holes that carry electric charge, and the simplest example of this, you start with the Einstein-Maxwell system. So F is the Maxwell field strength. And the most general spherically symmetric black hole is the so-called Reissner-Nordstrom solution. And the gravitational field describes a spherical body with mass m and charge q in the appropriate units. And there is an inner and outer horizon given by r plus minus. And I haven't written it down, but the Maxwell potential is just the Coulomb potential. In the quantum theory, Hawking tells us that such a black hole has associated with it an entropy and a temperature, which are given by those expressions. And we're going to be interested in the extremal limit, where in appropriate units the mass equals the charge. And then the temperature goes to 0. The black hole is stable, but there's a non-vanishing entropy given purely by the charge. And in the string theory, you can give a microscopic explanation for that, but I won't be doing that today. So that's Einstein-Maxwell theory. The black holes I'm going to be talking about are those encountered in supergravity. And in supergravity, you have more than one photon, and you also have scalar fields. And the idealized model I'll be looking at today is the maximal supergravity, which has 70 scalars and 28 photons. Now, it turns out that such supergravities have a global symmetry, which in this case is the non-compact version of the exceptional group E7. And the 70 scalars belong in a coset E7 over SU8. So the equations of motion have this global symmetry, which is sometimes called U-duality. And the field strengths and their joules transform, in this case, as a 56 of E7. The field strengths give you the electric charges, their joules give you the magnetic charges. So this unifies the electric and magnetic charges into an irreducible 56. And there's a similar story for other models, but let's focus on this one. So the solutions are in some ways similar to that Reissner-Nordstrom solution, except now we've got 56 charges instead of 1. There are also scalars to worry about. And you find that according to this attractor mechanism, as you go to the horizon, which is what gives you the entropy in the Hawking picture, you lose all memory of the values of the scalars at infinity, and the entropy depends only on the charges, just as in the Rice-Nordstrom case. Because the theory was invariant under that U-duality, the Bekenstein-Hawking entropy ought to be invariant also, and it's given by the square root of a quartic polynomial in the charges. And that quartic polynomial is invariant, in this case under E7, in general under whatever the U-duality group is. Now, if you know what a Jordan algebra is, fine. If you don't, here's a quick summary. And we're going to be looking specifically at cubic Jordan algebras. And as I said, if this is the first time you're seeing it, you probably won't gain a great deal by my talking about it. So let me skip on. What I really want to focus on is this FTS, Freudenthal triple system. And in humble language, the Freudenthal triple system is like a 2 by 2 matrix, except the off-diagonal entries, instead of being real numbers, are elements of the Jordan algebra. So they'll be octonionic in our case. And the three things I want to stress are that this system has a quadratic form, which we call xy, a quartic form, delta, and a triple product. That's the three important ingredients that we need: quadratic form, quartic form, triple product. And there's a symmetry of those objects, which we call the automorphism group of the Freudenthal triple system. And the one that we're going to be interested in is this one, the 56-dimensional representation of E7. And the Jordan algebra in this case happens to be the cubic Jordan algebra over the split octonions. So this is all well known to the supergravity black hole community. That's how you generate the automorphism group. An interesting thing about a Freudenthal triple system is it has a rank, which is like the generalization of the rank of a matrix. In fact, it has ranks 1, 2, 3, and 4, which depend on the values of this quartic polynomial, the quadratic form, and the triple product. So given a black hole, it will fall into one of these four classifications. Now, this is my day job. A hobby I've had lately is looking at the relation between black holes and quantum information theory. So I just want to briefly digress on that, because what I have to say was mentioned a few minutes ago in one of the other talks about 3-qubit entanglement. So I quickly sneaked in an extra slide here. But there's a one-to-one correspondence between the way you classify the black holes and the way you classify 3-qubit entanglement. And one thing we discovered coming from the black hole direction is that the 4 ways of entangling 3 qubits are just the ranks 1, 2, 3, and 4 of the Freudenthal triple system. That's not a result you'll find in the QI textbooks, but it's a very elegant way, I think, of classifying 3-qubit entanglement. Here's the G8Z state, which was described as the Borromean ring state. And here's the other 3-way entangled state, W. Then you have bipartite entanglement, separable, and null. And exactly the same picture appears on the black hole side. It depends on what fraction of supersymmetry the black hole preserves, but it can be 1, a half, a quarter, or an eighth. And the number of branes you need to wrap, which in this case is called n, corresponds to the number of kets. So this is a 4-charge black hole, 3, 2, 1, 0. And the reason why they match is that they're both described by ranks 1, 2, 3, and 4 of a Freudenthal triple system. So let's focus again on this FTS in the case of interest, where we've got 56 charges. Under this decomposition, they split as two singlets, a 27 and a 27 prime. And this is what the FTS looks like. The two singlets are in the diagonal. The 27 and the 27 prime are in the off diagonal. And they correspond to a cubic Jordan algebra over the split octonions. And what you can show, Hawking told us that the entropy of the black hole is 1/4 the area of the event horizon, at least to lowest order. And that turns out to be just the square root of this quartic polynomial in the charges delta. So all this is well known. And if you like, those 4 classes of black hole, or equivalently, the 4 classes of 3-qubit entanglement, can be represented by these coset orbits. So what do I mean by Freudenthal duality? Well, you remember we had a quartic form, we had a triple product, and we're going to define the Freudenthal dual of a black hole with charges x to be a black hole with charges x tilde, where x tilde is the triple product divided by the square root of the quartic norm. So it's a nonlinear transformation. If you compute the quadratic form with the dual and itself, you get the square root of delta. And it's an well, if you take its tilde twice, you get minus x. And the other thing of interest is that the quartic form is invariant. So here's a new discrete transformation that preserves the black hole entropy. What does it all mean? Well, we're struggling with that question, but for the moment I just want to impress on you that it leaves the entropy invariant. But more is to come. When you have electric and magnetic charges, Dirac told us that we have a quantization condition. And when you have dyons, which carry both electric and magnetic charge, you have what's called the Dirac-Schwinger-Zwanziger quantization condition. If they have electric charges q and p, then pq minus pq tilde minus p tilde q has to be an integer. And in the present context, that means that that U-duality group, instead of being defined over the real numbers, is now defined over the integers. So when I showed you that Reissner-Nordstrom black hole solution, Q was just any real number a priori, but in the quantum theory, it's quantized. So the group we're looking at is E77 over the integers. And in the FTS language, it's just telling you that the quadratic form of a black hole and another black hole has to be an integer. Now that makes things more subtle for our F duality, because if we start with a black hole whose charges are integers, we want to transform to another black hole whose charges are also integers. And that won't generically be the case. It will only be true for a subset of possible black holes. So let me just remind you again how it looks. We've got a black hole with 56 charges, Q0, P0, are two of them, the other 27 here and 27 there, where these belong to the integers and these belong to the cubic Jordan algebra over the split octonions, but now the integer split octonions. So they look like that. Now there's a theorem, and you can find the proof here, that you can always transform the most general black hole with 56 charges to something that depends on just 5 numbers: alpha, k, l, m, and j. And it looks like this. So this is the canonical one. You can reach any other black hole by transforming with E7. So this is the seed from which you get all the others. And in this case, the quartic norm looks like this. And by the way, irrespective of whether you go to the canonical form or in general, delta is now quantized itself. So the square of the horizon area is quantized. Now, one way of describing the black hole is by its entropy, which was the quartic invariant. But when you have integer charges, you can find other invariants that you can't find in the continuous case, and they're greatest common divisors. And I've called them D1, D2, D3, D4. Greatest common divisor of the charges x of this combination of this one and this one. And you can also define a fourth one that looks like that. Now, if you could reverse engineer, if someone gave you these invariants, you could recover the black hole that gave rise to them, then you would be able to classify all the black holes. And in certain circumstances, we can do that. We can do it in the case of the greater than 1/8 black holes, and we can do it for a subset of the 1/8 black holes that are called projective black holes. But so far, we haven't been able to do it in general. And I think there's good reasons for it. Some very smart mathematicians have attacked this problem in number theory and have not yet come up with the answer. So it would be very interesting to have it. Now, as I said, you have to take my word for it that in the case of one greater than 1/8 fraction of supersymmetry, knowledge of these invariants is enough to recover the black hole uniquely, so you can classify them according to the values of these invariants, but not in general, not for the 1/8 case, except in what are called projective black holes. And these are very counterintuitive, but you can find the proof in this paper that an element is said to be projective if its U-duality orbit contains a diagonally reduced element that looks like that and satisfies these conditions. Not exactly intuitive, but if that's the case, then you can classify them. How much time do I have left? Now, this requirement that the transformed black hole have integer charges means that not every black hole admits a Freudenthal dual, because requiring that x tilde is integer restricts us to the subset of black holes for which this quartic norm is a perfect square and for which it has these divisor properties. These were greatest common denominators of the cubic norm, the quadratic form, and the quartic norm. And so you have to satisfy all these conditions if your transformed solution is to be integer. Now you might ask, if this is a symmetry that leaves the Bekenstein-Hawking entropy invariant, And since U-duality, which in this case was E7, also leaves it invariant, can we be sure that we're not just doing a special case of a U-duality? And you can show that because it turns out that not all of those U-duality invariants are F-dual invariant. For example, the product D1, D3 is F-dual invariant, but D1 and D3 separately need not be. So that's enough to tell us this is a new symmetry and not just an old one in disguise. So a question one could ask is, if you compute not just the lowest order entropy, but the exact entropy to all orders of approximation, is the entropy invariant under F-duality? We know it has to be invariant under U-duality, but we've seen that not all U-duality invariants are F-duality invariants. And so at the moment, as things stand at the moment, that's still an open question. So there's lots of unanswered questions. We don't know why some black holes emit an F-dual and others don't, or how to characterize them. We don't know how to deal with the non-projective black holes. And there's all sorts of subtleties between U-duality and F-duality. So let me conclude with some open questions. In most cases, we saw that you can reverse engineer, and given the invariance, you can go back and determine the black hole uniquely. In general, you can't. And I think part of the problem is that we haven't yet got the full list of discrete invariants. I gave you 5, D1, D2, D3, D4, D4 prime. But there may be others, and again, we need a smart mathematician to tell us how many there are. If we knew them all, that might be some way towards classifying the black holes. When, in general, is delta a perfect square? You can do a case-by-case analysis, look at its charges of the black hole, and when it is a perfect square, you're in with a chance of defining the F-dual, and if it isn't, you're not. But it would be nice if we had some better criterion for deciding ahead of time when you're likely to get a perfect square. And if we did all that, perhaps the hardest question of all, what's the physical significance of it? In certain cases, you can show that the black hole entropy depends only on D2 and delta, which are F-dual. So for that subclass of black hole, you know that the entropy is F-dual invariant. And perhaps a better way of tackling the whole problem is to step back and ask, why is this just a symmetry of the solution? Well, was it not a symmetry of the Lagrangian you started with? And at first we thought the answer was no, but we've just done some recent work with Ferrara and Marani, which suggests that, in fact, defined in the right way, is a symmetry of a previously unnoticed symmetry of supergravity. So perhaps if we understand that better, we'll understand the black hole one better as well. Thank you.
Thanks to Mike's masterful recovery and speedy delivery, we have time for a couple of questions.
Yes?
What do you see as the effect on quantum information theory of this kind of correspondence with the black holes?
Well, that's an interesting story in its own right, which I could have spoken about. I was tempted to speak about, but chose not to. The first clue that there was a link between the two was this observation that the invariant that gives you the black hole entropy is also an entanglement measure, at least in the case of 3 qubits. In the case of 3 qubits, the quantity delta is something introduced by Cayley in 1845, Cayley's hyperdeterminant. So both the 3-qubit entanglement measure and the black hole entropy are given by Cayley's hyperdeterminant. But that turned out to be just the tip of an iceberg, and we've now got a whole dictionary between phenomena in quantum information theory and phenomena in black holes. I have to admit it's a mathematical connection, so it's useful to use tricks. Using tricks on one side, we can solve problems on the other. But as far as I know, there's no physical connection, at least we haven't seen it yet. But for example, let me give you an example of its utility. 3 qubits are well understood. 4 qubits, classifying in the way that 4 qubits are entangled, is 2 orders of magnitude more difficult than 3. And we were able to show, we borrowed a result from black hole physics that the corresponding black holes fall into 31 different orbits. And there's something called the constant-Sakaguchi theorem, which relates nilpotent orbits of the groups that appear in black hole physics to the nilpotent orbits of the groups that appear in quantum information theory, which is just what we need. And in that way, we were able to show that 4 qubits can be entangled in 31 different ways, which was a new result. So it was nice not just to recover what the quantum information people already knew, but we can go on and make statements that they didn't know. Now, where it all leads is an open question. I don't know what more we can do, but we'll... One thing I should mention in supergravity is that not only do you encounter E7 and E8, but you encounter the infinite dimensional extensions, E9, E10, E11. And my collaborator, Lavon Lawston, has found that they may also have a role to play in quantum information theory, which I think would be interesting.
Okay, if there are no further questions, let's thank Mike again.